being shut down or inoperable. And so it was the investment risk, really not the public safety risk, that was of concern. And it was also, actually EPRI did a survey of a bunch of the plant operators, and the consensus was that these plants were too big, they were too complex, they were too hard to manage, they were side. And so Weinberg's conclusion was we really need to focus on a whole new generation of electric dynamics. Simpler, use more safe features. And he actually did a study of some of the designs that were beginning to be worked at that time, particularly focused on what was called the PIUS design and also the high-temperature modular gas reactor. And he cited those as two examples of the kinds of systems that water-based recycling are on. So here's just a sampler. This is my acronym HELL slide. Those are all acronyms of various small reactors that are being developed around the world. You can see they span the whole gamut from water reactor systems, very conventional designs up to very non-conventional designs. A lot of countries involved. Some of them are countries, some are not. The ones in red are those designs being worked in the U.S. right now. This is about, I think this represents about 30 out of 50 or so that are on the books as being worked by various groups. Of course, the maturity of the various concepts and designs vary a lot here, and therefore the deployment schedule will vary a lot. Anyway, gives you some idea of the variety of designs out there. And we're always finding new ones just about every month. In the United States, there were a number of designs being worked. I'm going to try to capture those in the next three slides, categorized by what I think are the level of maturity or potential for deployment. So these are the three front-running light water reactor designs that are out there. On the left is the IRIS reactor. This is being worked by a Westinghouse-led international consortium, actually. A lot of members involved there. It is a 335 megawatt electric size plant. I come from Tennessee, so I'm not used to the dry climate out here. So mPower being offered by Babcock and Wilcox in the middle, that's a 100 design. And then on the new scale, which is a 40. No, the IRIS vessel is about 3 meters tall. The mPower is also about 23, maybe 22. And the new scale is about 14, so it's quite a bit smaller. Now, what's interesting there are some differences. Obviously, the power output's very different, but there's a whole lot of similarities. They're all what is called integral primary system reactors, and I'll explain that a little bit more because that's a classic example of a deliberately small reactor. So they're all, from a thermohydraulics point of view, very similar in that they're integral primary systems. They also all use helical coil steam generators, once through steam generators. They're very different in how they would expect to deploy these. The IRIS is looking pretty much at single units or maybe 2 twin units, but you still would have a dedicated power conversion system for each reactor. So it would look more like the big plants, and it would be a standalone. The Babcock and Wilcox, well, let me say NuScale on the far right, they're taking the other extreme, and they're saying their reference deployment plant would be a 500 megawatt plant that was produced from 12 of those modules. So you literally line up 12 modules, plug and play. Each module has its own turbine generator set, so each one's sort of standalone, but they plug and play into a galley of modules. And then the mPower in the middle kind of splits the difference. Their scenario is also a 500 megawatt plant that would be comprised of 4 reactors feeding 2 steam generator sets. So it'll be real interesting to see how these designs play out, and particularly how the business model that each one is assuming will play out. As we move a little further down range, these are 3 gas-cooled designs that are being worked. These are all candidate designs for the next generation nuclear plant in GMP. We've got the General Atomics version, the PBMR, and then the Riva Antares. And then moving, but I think it's a little further out, will be the liquid metal systems. And these are fast spectrum systems that offer other advantages, particularly the very long-lived cores, potential for no on-site refueling type systems. You've got the General Electric Prism, which has been around for actually quite a long time. Actually, I like the Prism because that's where I first got really intrigued with modular plants. And they were the first really vendor-motivated design back in the early 80s as part of the Advanced Liquid Metal Reactor program. That the first time I saw a plant, I've been working on Clinch River reactor, which is sort of the traditional scale up to mega size. GE came in and said, no, the way to go are small modular plants. And they envisioned a plant that would be comprised of 9 of these modules feeding 3 turbine generator sets, I think. I thought, that's kind of cool because by keeping it small, you incorporate a lot of features, which I'll talk about. So then we have the 4S, it's a little 10 megawatt beast. And then if you want to look way out, we got the Hyperion power module, which is pretty much undefined at this time. It uses a uranium hydride fuel, uses potassium heat pipes for heat removal, uses hydrogen dissociation for control. Really exotic. So there is really emerging very rapidly, literally this year, a lot of interest in small plants. Actually been interest around the world for a couple decades, even